Hi there, and thank you for tuning in to this midterm solution video. Let's get started. For the first problem, you have a bunch of definitions or descriptions. So part A, what does it mean for a function to be a linear map between vector spaces? So you can't just give descriptions like, oh, it's linear if it's preserved something. You have to give a formal mathematical definition. So probably the easiest way to do that is to say that T of AV plus BW equals AT of V plus BT of W, and this is for all vectors V and W in V, and scalars A and B. Now this is not the only way you could do it. I think some of you might have done this in two steps, and at least one of you did. You could say T of V plus W equals T of V plus T of W, and T of, say, AV equals AT of V, and then same for all VW and A. So either of these answers is fine. Okay, to find the kernel, so this is the set of all vectors in V such that T times V is 0. That is the 0 vector in W. If you said it in words, that's fine as well. But I think it's just easier to say it like this. So what does it mean for a second order differential equation to be linear? So if you say things like it doesn't have powers or things like that, that's not a precise definition. I think a precise definition would be it has the form, or it can be written as A of t times y double prime plus b of t y prime plus c of t y equals d of t. Now you don't need to put the a of t here because some people like to divide out by this, so make this monic, and then you just put functions here. So what does it mean for a second order linear differential equation to be homogeneous? That means that d of t equals 0. What can we say about the structure of the set of solutions to a second order linear differential equation? So homogeneous, and let's start with homogeneous first. It is a 2D vector space. Or if you prefer, you can write it as the form C1y1 plus C2y2. And then inhomogeneous, it's a 2D affine space. I give you full credit if you said vector space, affine space, but to be a little more precise, it has the form C1y1 plus C2y2 plus some yp of t, where this is any particular solution. But vector space and affine space, that's really what I was looking for. Problem 2. Okay, this was trickier, or this ended up being trickier than I intended it to be. So I think it's important to make sure that we get these concepts. So for each of these subsets, so this is a 4-dimensional vector space. Determine whether or not it's linearly independent, spans, and is a basis. So first of all, before we get started, I want to remind everybody that S is a basis if and only if S is linearly independent and spans. So some of you said things like, in one of these parts, you said, oh, it's yes, it's linearly independent, yes, it spans, but it's not a basis. Or you said it's a basis, but it only has one of these. This is an if and only if. So I want to make sure that you understand that concept first. Next, let's go through here. So this, it definitely spans, because you can see, you can write every polynomial of degree at most 3 using these guys, right? You don't need 0. Because you don't need 0, this is linearly dependent. So this spans, and it's linearly dependent, so not linearly independent. And remember that the actual formal definition of linearly dependent means that there is a way to write a naught times 0, or I don't know how to, yeah, sure, a naught times 0 plus b naught times 1 plus b1 times x plus b2 times x squared plus b3 x3. So there is some way to write the zero vector using these guys where not all constants are 0. And you can see how to do that. A naught can be anything. So for example, if this is equal to 1 and all of these are 0, then that's how you do it. But you don't need to show this, but I'm explaining why it's linearly dependent. Okay, next, this one. So here we have 4 vectors. And so let's see, does this span? And if you think about this carefully, you realize that yes, this is going to span because any, so if you take linear combinations of these 4, if you start with this one, you subtract off x squared, x, and 1, you get x cubed, and now you get these 3 vectors that we've already said clearly span. So you can definitely generate any vector using these guys. So this is going to span. And now if we have a set of 4 vectors that spans a 4-dimensional space, it has to be linearly independent. If you don't quite see that, what you can do is you could say, well, what about, let's see, a3 times x cubed. So here's another way to see why it's linearly independent, plus a2x2 plus a1x plus a naught equals 0. So suppose you have something like this that is 0. How do you prove that? How do you show that all of these coefficients have to be 0? So, well, I wasn't prepared to actually do that. You don't need to prove this, but let's just do it for practice anyways. Okay, so clearly if this is equal to 0, then a3 times 1 has to be equal to a naught. So in other words, a naught has to be negative a3. So let me write negative a3. Okay, so now what else? We also have that a2, so a3 times x squared has to be negative a2 times x squared. So in other words, this also has to be negative a3. Maybe I should have prepared it a little differently. And similarly, if this is 0, then a3x has to be equal to a1x, so a1x has to be negative a3x. So this is negative a3x equals 0. So now, why does a3 have to be 0? So, well, a3 has to be 0 because if you look at the x cubed term here, that better be 0 because there's no x cubed over here. So a3 has to be 0. So this entire, so yes, a1, a2, and a3 all have to be equal to 0. Okay, so that's more than you had to do. Finally, the last one, what I want you to notice, I try to make this as obvious as possible, not everybody saw it. This vector is just that one plus that one. So what we have is we have one vector here, another one which is not a scalar, but then this doesn't add us anything. So this is redundant. So that means that it will not be linearly independent, and because this vector is not needed, we only have 3 vectors, so it's not going to span. It will not span, so it's not a basis. Oh, and I probably should have said up here, it spans, and it's, as I said, it's linearly independent, so it is a basis. Okay, so that's those 2 problems. Problem 3, solve the following differential equations. This first one, I want you to look at this and say y equals yh plus yp. And I want you to recognize by inspection that yh is c e to the minus 2t. I think most of you did that. And then for a particular solution, yp equals some constant times e to the 3t. So it has to have the same form as this function here. So we take this and we plug it back in. Let's see. So yp prime equals 3a I think everyone got this right, except maybe it missed a scalar in some part. So I'm going to do this quickly. So if you plug this back in, as if you plug it back into here, what do you get? You get a 3a e to the 3t plus 2a e to the 3t. Again, this is y prime, this is y, 2y, and this is e to the 3t. And so you get 5a e to the 3t equals e to the 3t. So a equals 1/5. So your answer for this one is y equals c e to the negative 2t plus 1/5 e to the 3t. Now I will say, I think everyone in this class, as I said, got this right, or like messed up the algebra in here, and so pat yourself on the back, because I taught honors differential equations I think just over a year ago in the spring, and I remember I would put problems like this on the final exam, and absolutely not everybody would get this right. Like I'd maybe have a third of the people who didn't know how to solve the homogeneous equation. So I mean, that tells me that I made this exam hard, and so if you did poorly on this, or if you didn't like your score, I mean, this is, from what I can tell, comparable to like an honors style class so don't get down if you see a low score. Again, I as I said in my email, I did make this hard. Let's do the second one right here. Y double prime minus 4y equals t squared. So once again, y equals yh plus yp. And the homogeneous solution here is, again, I want you to be able to do this in your head. This is c1 e to the 2t plus c2 e to the negative 2t. Again, I think almost everyone or everybody got this right. In that same honors class I was talking about, I put a problem just like this in the final, and I want to say at least a third just didn't even know how to get the homogeneous right. And it's not like I hadn't been emphasizing that throughout the class, saying the same thing that I'm telling you guys. So I guess what I'm saying is, you guys are really good. So it's easy to look at a score and be discouraged, but please don't. Okay, so homogeneous, particular solution. So yp of t, what you have to do here is you can't just do at squared. You have to do at squared plus bt plus c. Now you got to plug that thing into here. So two derivatives of this, yp double prime equals 2a, sorry, just 2a. So if we plug this into here, we get 2a minus 4 at squared plus bt plus c equals t squared. Did I do that right? Okay, so we have, let's, something times t squared plus something times t plus something equals t squared. So so what goes in here? Let's see. So we have a negative 4a, which goes there, and then we're going to have a negative 4b that goes here, and then we're going to have a 2a minus 4c that goes here. This has to equal 1, so a equals negative 1/4. This has to equal 0, so b equals 0, and this has to equal 0. So what that means is 2a, which is negative 1/2 minus 4c equals 0. That means that c equals negative 1/8. So that means our solution up here is going to be c1 e to the 2t plus c2 e to the minus 2t minus 1/4 t squared minus 1/8. Finally, this last one. So I want you to look at this and recognize that is Cauchy-Euler. I think at least one of you used the power series method, and I think got it right. But you don't have to do it that way, or you shouldn't do it that way. You should look at this and say, well, for every derivative of y, there's a power of t. So we can assume let's put this over here. See, we can assume that the solution of the form y of t equals t to the r. And let's plug it back in here. So y prime equals r t to the r minus 1. Y double prime equals r times r minus 1 times t to the r minus 2. So we plug that. So let's just plug this whole thing back in here, and we get t squared times this is r minus 1, not t squared is t to the r, plus 2t times this is 2r t to the r, minus 12 t to the r equals 0. So we have this, and we get r minus 1 plus 2r minus 12 times t to the r equals 0. So that thing better be equal to 0. And what do we get? We get r squared minus r plus 2r. So that is plus r minus 12 equals 0. So we get r minus 3, r minus 4. One of these is positive. Which one is it? It's going to be that one. So that means that r equals 3, r equals negative 4. So y of t equals c1 e to the 3t plus c2 e to the negative 4t. And that is that. Okay, problem 4. Find a differential operator, L, whose kernel has these two functions as a basis. So let's work backwards a little bit. And so what differential equation has these two things as a basis? So that's going to be y double prime plus 4y equals 0. So the differential operator is going to be d squared d t squared plus 4. Because again, you can write this as d squared dt squared plus 4 times y equals 0. Okay, so that's the operator. Find a basis. I think I made. I'm trying to remember. I think I made this part D 2 points and part A 2 points, and the rest 1 point. Find a basis consisting of real valued functions. So of course you can do sines and cosines. So cosine of 2t, sine of 2t. Write down a finite spanning set that is not a basis. Well, you can just add anything you want to here, and it will work. Well, so I should say anything you want that's a solution. Not, you can't just add anything. Sine of 2t, so let's add e to the 2it. There we go. It spans, but it's not a basis because it's not linearly independent. So write down a differential equation whose solution space, well, right there. And then write down an equation whose general solution is the affine space here. So now you want this to be a particular solution. So if if you plug 1 into here, you get 0 plus 4 is 4. So you get y double prime plus 4y equals 4. And that is that. Okay, problem 5. Solve the following differential equation using the power series method. So let's write down our function y of x equals n equals 0 to infinity, a n x to the n, y prime equals n equals 0 to infinity, n a n x to the n minus 1, and y double prime equals of x equals n equals 0 to infinity, n minus 1, a n x to the n minus 2. Okay, so now let's plug this back in. This first term, y double prime, we have it right here. So that's going to be equals 0 to infinity. Actually, I'm going to do what most of you did fine, is I'm going to shift this right now. So let's shift this by 2. So this is going to be n plus 2, n plus 1, a n plus 2, x to the n. And I'm going to start from 0 because we don't need to go down to negative 2 because of those two terms. And then minus X squared times this. Let's just bump this up to n. So n equals 0 to infinity, n minus 1, a n x to the n. Now plus 4x times this. So let's just take a 4x in front of here, and that bump that up to n. So plus n equals 0 to infinity, 4n a n x to the n minus n equals 0 to infinity. Let's take a 6 in front of here. 6 a n x to the n equals 0. Okay, so what we have is n equals 0 to infinity of a whole bunch of stuff times x to the n equals 0. So we have n plus 2, n plus 1, a n plus 2. And then we have minus n minus 1. So we're going to have minus a whole bunch of things with an a to the n. So let me do a to the n there. So we have a 4n right there, minus 4n. So this is plus, so that's minus minus. We have a minus here, so it's going to be a plus 6. So plus 6. Okay, so now, of course, this thing here has to be equal to 0. So that means that n plus 2, n plus 1, a n plus 2 equals, so this is, so let's move this over here. This is n squared minus 5n plus 6 times a n. So that is, what is that? N minus 2, n minus 3, a n. So that means that we get a n plus 2 equals n minus 2, n minus 3 over n plus 2, n plus 1, a n. So there's the recurrence relation. So if you fix a naught, then a2, so we get a2 by saying n equals 0. a2 equals, so let's plug in n equals 0 into here. We get negative 2, we get 6. On the top, we get 2 in the bottom, so 6 over 2 is 3 a naught. And then when n equals 2, we see we're going to get a 0 on top, so we get a4 equals 0 times a2. So then all the other even terms are going to be 0. Next, let's fix a1, and then when n equals 1, we get that a3. So a3, when n equals 1, we get negative 2 times negative, hold on. All right, 1 minus 2 is negative 1 times negative 2. So that's positive 2. And the bottom we get 3 times 2, which is 6. So 2 over 6 is 1/3, a1. And then when n equals 3, we're going to get that a5 is 0, a3, because 3 is a root of this top. So, okay, so what that means that what we get is we get y1 is a naught plus 3a naught x squared, and y2 is a1 plus 1/3 a1 x cubed. So I say find a basis for the solution space. So your basis is going to be 1 plus 3x squared, and this a1 should be a1x. I wonder if anyone caught that. So then x plus 1/3 x cubed. So I kept that. I didn't go back and edit that because I'm showing you that we all make mistakes, and a lot of the mistakes we will catch later along the way when something looks weird. That's what it looks like. I think it's helpful for you to see me make mistakes like that, and notice them as we move on. So finally, the general solution is a naught times 1 plus 3x squared plus a1 times this. Now, a couple of you don't like fractions like me, so you can multiply, if you want to multiply this thing by 3 and get 3x plus x cubed, that's perfectly fine as well. Or you could just say x plus 1/3 x cubed. You know, the 1/3 gets absorbed into this a1. Okay, so that is that problem, and now we've got one more. Okay, I like this last one because to do it, it would be a little bit messy, but what I have you do is just set up the integrals, and so you have to really understand the concepts. And a lot of you just completely nailed this question. That's awesome. And what I want is I want everybody to fully understand this. So make sure that you do not finish this video today until you fully understand how you do this and what mistakes you made, if any. So we have a vector space of dimension 3. The polynomials of degree at most 2. And I define an inner product. We are going to see that inner product actually next week in class. And I'm telling you that these functions form a basis. And they're called Hermite polynomials. So again, we're going to see these, they come up in physics. So this basis is actually orthogonal with respect to this inner product above. And this can be verified by computing 3 integrals. Now, most of you got this right, and that was so good to see. Because it's, so what does this mean when I say they're orthogonal? Well, that means that H0 and the inner product of H0 and H1 is 0, and that, by definition, is 1 times 2x e to the minus x squared dx. That is 0. It means that H0 and H2 has to be 0, so that inner product, we take the product of these two functions. So negative infinity to infinity, 4x squared minus 2 e to the minus x squared dx, that has to be 0. And finally, the last one is H1 and H3, their inner product has to be 0. So that means that 2x times 4x squared minus 2, e to the negative x squared dx equals 0. Now, a lot of you got this right and probably aren't happy about your score on the midterm, but let me tell you, I've given problems like this before, and I've seen people get it wrong in so many ways. So the fact that most everyone in this class did this part perfectly, that means you understand it, and I noticed that. And I'm the one deciding final grades at the end. So don't worry about numerical scores as much as making sure that you understand the material and you get and you're keeping your head above water. And let me know if you have questions. Again, I'm available every morning and every evening. Okay, so next, find the norm with respect to this inner product of it. And I just wanted you to do H naught, not the other two. So the norm of H naught of x is the square root of H naught. I'm going to stop writing the of x. H naught with H naught. And so this is the integral from negative infinity to infinity of the function 1. So, I don't know, 1 times 1 e to the negative x squared dx. And, I should say it's the square root of that. And so, and I told you that this thing under here is the square root of pi, so that's the square root of the square root of pi. If you left it like that, that's fine. I think most of you wrote things like pi to the 1/4 or the 4th root of pi. That's even better. Okay, so the function 1 does not have norm 1, it has norm 4th root of pi. Okay, so next, write down an orthonormal basis in terms of the Hermite polynomials and integrals. So what we have here is an orthogonal basis. So the picture you should have in your mind with this is that you got these three functions that are well, they're supposed to be right angles, but they are not unit length. So if this is H naught, if this is H1, and this is H2, then what you want are you want scalar multiples of these things that are unit length. So that's going to be H naught divided by the norm of H naught. This is H2 divided by the norm of H2, and of course this is over here is H1 divided by the norm of H1. So that means, okay, so your basis is going to be H1, that's 1 divided by the norm of H naught, which you've already computed, which is pi to the 1/4. The next one is H2, or H1 divided by the norm of H1, and remember that we're going to use this formula. You just take the inner product of the function with itself. So that means we are integrating from negative infinity to infinity of 4x squared e to the minus x squared dx, and I make sure I take the root of that. And finally, the last one is H2, which is 4x squared minus 2 divided by the square root of the norm of the function with itself. So that's just, so now we have to integrate 4x squared minus 2 squared e to the minus x squared dx. And there is our answer. So obviously I didn't want you to compute these, but I wanted you to understand conceptually how you take an orthogonal basis and turn it into an orthonormal one, and how you do that, and how you abstract the norm from this inner product. And I was pleased with the number of people who got this right. And obviously I want everybody to get it right, but I've taught this class before, and I feel like people did really well in this exam. Okay, so the last part, you got a function. We're decomposing this function into this basis. So each of these is like the projection of this function onto those components, but of course, because these are not normal vectors, you have to you got to modify it a little bit. So C naught is just the projection of P of x onto H naught. I should stop writing the of x's, but then we have to divide by H naught of x and H naught of x. So I'll stop writing the of x's after this. So this is the integral. I'm going to start writing the integral over R instead of negative infinity to infinity. It's easier to write and to say. It means the same thing. So it's the integral over the real line of 1 plus x squared times 1 times e to the minus x squared dx divided by, we know what this is. This is pi. This is the square root of pi. Similarly, C1 is the integral of P and H1 over, the inner product over H1 with H1. So we're integrating over the real numbers of 1 plus x squared times H1 is 2x times e to the minus x squared dx. And we got to divide that by the integral over the real line of, I can't go lower because if I go lower, I have the little bar where my controls, my pause and record button is, and I'll hit that if I go lower. So 2x squared is 4x squared. Oh well, e to the minus x squared dx. And finally, C2 is inner product of P and H2 divided by inner product of H2 with H2, which is the integral over the real line of 1 plus x squared times, what's that other function? h2 is 4x squared minus 2 e to the minus x squared dx over the inner product of, so again, this thing times itself, so that is 4x squared minus 2 squared over the real line, e to the minus x squared dx. And there we have it. Please let me know if you have any questions. Again, I am available every day, morning and evening. Hope to hear from you.